This week's lesson is Lesson 10.8, the probability of compound events. This will probably be a little bit of a lengthier video, but your assignments I think are relatively short this week. So make sure that at any point during the video, if you need to pause it, copy some things down, re-listen to some parts, that you do so. Let's begin with some key vocabulary. The sample space is the set of the possible outcomes in a probability experiment. So if you roll a die, the sample space would be the possible outcomes, which would be 1, 2, 3, 4, 5, or 6. Let's say you're going to choose a tile from a set of Scrabble tiles. The sample space would be all the tiles that you could choose from. A tree diagram is one way to visually represent the sample space. This tends to work out a little bit better when we have a small sample space versus a really large sample space. Because when we talk about compound or composite events, just like when we talked about composite figures, consist of two or more simple events in this case, like composite figures were two or more shapes put together. So if we talk about some compound events, that could be rolling two die, which has 36 possible outcomes. Not a huge number of outcomes, but the tree diagram can get really complicated for that. Or if you go to a sub shop or you go to an ice cream shop, all the possible combinations, sandwiches or subs or ice cream sundaes, you would have a lot of different possible combinations. So trying to make a tree diagram for that might not be as easy. So I want to show you an example of a tree diagram, do three different problems, and then actually get into some problems that don't involve drawing tree diagrams, but involve finding the probability of compound events. So the first example says a diner offers coffee, tea, and juice to its customers. They also offer bagels, muffins, and danishes. How many different combinations can be made if the customers must select one beverage and one bread option? List the sample space. And anytime it asks you to list all of the possible outcomes, to list the sample space, for those kind of things, you definitely want to create a tree diagram to help keep your information organized. So the first thing I always do is I list my events across the top. So in this case, our events are the beverage that we have to choose, as well as the bread that we have to choose. And again, those are the events. Those are the things we have to choose from. Then we list the outcomes going down. So for the beverage, we have three possible outcomes. We can choose either coffee, tea, or juice. So we list those going down and we leave a little bit of space between them because we're going to have branches, just like a tree, coming off of each of those. Now let's just start with coffee. Let's say I choose coffee. The bread that I have, I still have three outcomes. I can choose a bagel, a muffin, or a Danish. So I still have three possible outcomes here. So I have three branches coming off of that. Now I do want to mention when I go to list my sample space, that's going to be this over here. That's me taking my beverage and bread choice and listing those out. And you can use abbreviations. It's easy for me to type this out, but as you do some examples, you can use abbreviations for those. So one option in my sample space is coffee and bagel. So that's following this branch here, coffee, bagel. Then coffee, I could also have a muffin. So coffee muffin and then coffee Danish, which would be this last one up here. So that is right up here, three possible outcomes. Okay, or three items in our sample space. Now let's say I choose tea as my beverage. I still have those same three possible outcomes, bagel, muffin, Danish. The only thing that's going to be different with my three possible outcomes here is instead of having coffee, I have tea. So it's tea bagel, tea muffin, tea Danish, but I have another three possible outcomes. And then we go down to juice. Let's say I choose juice. I still have the same three possible outcomes, bagel, muffin, Danish, and I replace coffee and tea with juice here. So we've got juice, bagel, juice, muffin, juice, Danish. So I have another three possible outcomes for a total of nine outcomes, or nine elements in my sample space. And this makes sense for us as well. One way that we could figure out the total number of outcomes without listing all the possible outcomes or listing the sample space would be to look at my two events. In this case, my first event is the beverage, and I have three choices for beverage. And then for our bread, we had three possible choices as well. And if I take, I'm going to use parentheses for multiplication. If I take 3 times 3, that gets me 9 possible outcomes as well. Now that's not useful if it says list all the outcomes because you still need to list them, although it does give us an idea of how many possible outcomes we will have. So let's look at another example. And again, you may want to jot this down. A deli offers white or rye bread, ham or turkey, and Swiss cheddar or provolone cheese. And we're simplifying this. I mean, if you go to an actual deli, you'd have a lot more choices. Draw a tree diagram to find the sample space for a sandwich consisting of one type of bread, one type of meat, and one type of cheese. Now, I did not use abbreviations, at least not in my tree diagram. I did for my sample space, so feel free to use those abbreviations as well. So the first thing I want to do is list my events across the top. And my 3 events here are my bread, meat, and cheese. Again, we could complicate things by saying, well, we're not going to choose a meat. Maybe we don't want meat on our sandwich, or maybe we don't want cheese, whatever. But we're not going to go crazy here. We're going to assume every person chooses a bread, a meat, and a cheese. So let's list the outcomes for each. And I should mention as well, it doesn't matter if you list them in this order. So it's going to look a little different if I would list meat, cheese, then bread. But that being said, you would still have the same number of elements in your sample space. The tree diagram would just look slightly different. But I like to just kind of go in the order in which it's written. So for bread, we have 2 choices, white or rye. For meat, we have ham or turkey. So off of white bread, I've got ham and turkey. Off of rye bread, I have ham and turkey. And then off of each of these guys, there's 4 of them here, I have 3 choices for cheese. So I'm going to list Swiss, cheddar, and provolone off of each of these. It's really important that if I have 3 branches off of this guy, I have the same number of choices for this one, and this one as well. Now, when I go to list my sample space, I'm going to follow these branches and I'll follow a few of these for us so we can show it. But my first element, my sample space, is WHS, which represents white bread, ham, and then Swiss. So WHS is going to be this guy right here. And then I have WHC, which would be this guy right here. So white bread, ham, and then cheddar. And then in blue, the next one is white ham and then provolone, WHP, is going to be following this guy through here. What I like to do is draw this line from each of these so I know that I'm including every element of my sample space. And then still choosing white bread, but instead turkey, we'd have white turkey Swiss, white turkey cheddar, white turkey provolone. You don't need the commas between these. I just included them there. So you could have just WTP. Then if I don't choose white bread, I'm going to choose rye. So I've got rye ham Swiss, rye ham cheddar, rye ham provolone, rye turkey Swiss, rye turkey cheddar, and rye turkey provolone. Again, it doesn't matter if they're in this specific order. They can really go in any order we wish to write these. What I'm going to mention here too is that if I want to figure out the total number of outcomes, which is my first question down below here, I can keep in mind that I had 2 choices for bread, I had 2 choices for meat, and I had 3 choices for cheese. And if I take 2 times 2 times 3, that's going to get me 12 possible outcomes. If I count up how many elements I have here underneath my sample space, there are 12 possible outcomes. So that's what we should have in this box right here. So let's go ahead and delete that. Now, the next questions are interesting ones related to probability based on our tree diagram. So it says, what is the probability of a customer choosing white bread and ham? That means in my sample space, I need a W and an H. So I'm going to highlight this in yellow. These 3 outcomes have white bread and ham. Those are the only ones out of the 12. Well, that is 3 out of the 12 possible outcomes, which reduces to 1/4, which is 25%. Then it says, what is the probability of a customer choosing turkey and provolone cheese? That means I need a T and a P in my outcome or sample space. So that's going to be this outcome here and this outcome here. But those are the only 2 that have both turkey and provolone. So this one's going to be 2 out of our 12 possible outcomes, which reduces to 1/6, which is 16.6 repeating percent, or about 16.7%. Remember, do 1 divided by 6 to get 0.16 repeating, which is about 16.6 or 16.7%. All right, so number 2, a coin is tossed 3 times. Draw a tree diagram to show the sample space. So a lot of times I have students who want to list like, um, heads and tails across the top. Those are not my events. My events are the three tosses of the coin. You can even say like coin one, coin two, coin three, but in this case, it's the same coin being tossed three times. So toss one, two, and three are my events. Now the outcomes are heads and tails for each of those events. So for toss one, I could get heads or tails. For toss two, if I get heads, I could get heads or tails. If on toss one I got tails, I could also get heads or tails. And then if I had heads and then heads, I could get heads or tails on my third toss, and so forth. So off of each of these elements, each of these outcomes, I'm going to have H and T to represent heads and tails. So my sample space is going to include heads, 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 tails, heads, tails, heads, heads, tails, 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 heads, heads, tails, heads, tails, 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 heads, and tails, tails, tails. Try saying that again 3 times fast. But we've got 8 total outcomes in our sample space, which makes sense because on toss 1 we had 2 outcomes, we had 2 outcomes on toss 2, and we had 2 outcomes on toss 3. 2 times 2 times 2 gets us 8. So the question below says, what is the probability of all coins landing on heads? Definitely a good question for us. If we take a look at our chart, we only have one outcome where all 3 coins land on heads. And so that is going to be 1 out of our 8 possible outcomes, which is 12.5%. Now you're going to notice that this next example is really the same tree diagram, except it doesn't have H and T, and you'll see in a moment. Number 3, Mr. and Mrs. Rodriguez are expecting triplets. The chance of each child being a boy is 50%, and the chance of each child being a girl is 50%. Draw a tree diagram to show the sample space. So you talked about something similar to this in science when you did your genetics unit. You probably did some Punnett squares and things like that. So this is not unusual for you to have seen at some point, but maybe not in the form of a tree diagram. But a Punnett square is essentially one kind of tree diagram. So if we have triplet 1, triplet 2, and triplet 3, those are my events, our 3 children that are being born. So instead of having H and T down below here as my outcomes, it's B and G. B for boy, G for girl. So the first triplet could be either a boy or a girl. Second triplet off of each of these guys will be boy or girl. And then off of each of these for triplet 3, the third triplet could be a boy or a girl as well. And this also gives us an indication of the order in which they're born, which technically doesn't really matter too much, although some would disagree. But for example, if we have BBG, that's really the same as BGB. You've got 2 boys, 1 girl. It's just the order in which they're born that's different here. And that will come into play when we do some of our probabilities down below. So our sample space would be boy, 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 girl, boy, girl, boy, boy, girl, 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 boy, boy, girl, boy, girl, 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 boy, and girl, girl, girl. We again, just like our heads and tails question, have 8 possible outcomes since you have 2 possible outcomes for each triplet. 2 times 2 times 2 is 8. So down below it says, what is the probability that all 3 children will be girls? Well, I'll highlight that outcome in yellow. There is only one possible outcome, kind of like in the last question, what's the chance of all 3 coins landing on heads or tails? Well, it's just going to be 1 out of 8, which is 12.5%. What is the probability of 2 boys and 1 girl? So let's go through. We need 2 boys, 1 girl. So that's going to be this outcome, and this outcome. 2 boys, 1 girl, 2 B's, 1 G. That's going to be 3 out of our 8 possible outcomes. 3 divided by 8 is 0.375, which is 37.5%. And then finally, what is the probability of at least 1 boy? Well, that's going to be all possible outcomes with the exception of the GGG. So that's going to be 7 out of 8. And 7/8 is 87.5%. So all but where all 3 are girls. Okay, so there's a pretty great chance that at least one of those kids will be a boy, or if we would go the opposite way, at least one of the kids would be a girl. All right, so let's shift gears a little bit to some problems related to calculating with probabilities. So we're not going to see too much more in the way of tree diagrams. For this week, I didn't make any assignments with tree diagrams. It doesn't mean you may not see it in the future, But for this week, there's no specific examples where you're asked to find or draw a tree diagram. So let's talk a little bit about independent versus dependent events. These are both used when you select more than one item, by the way. A lot of times you'll see the word and used versus or. You might see something then something as well. It may not use the word and. But when we talk about independent and dependent events, it's more than one event occurring. Whereas in the past, when we talked about probability, we just did simple probability. So maybe we had a jar of marbles. What was the probability of selecting a red marble? We may have also had problems like what's the probability of selecting a red or blue marble? But again, you were still only selecting one marble. The difference here is that we're going to select more than one marble, maybe two marbles, maybe three marbles, but you're going to select more than one marble or more than one item. And we will multiply to find our probabilities as well. So independent events, that's when the outcome of one event does not affect the outcome of the second event. This is with replacement. So I take out a marble and then I replace it. So an example would be Sully selects a marble from a bag, she replaces it and then selects a second marble. Those are independent events. They don't impact each other. So if you want to find the probability of two independent events, take the probability of the first event and multiply it by the probability of the second event. So you write down the two probabilities and you multiply them. Dependent events are when the outcome of one event does affect the outcome of the second event. So this occurs when the item is not replaced. So Irene selects a marble from a bag, she does not replace it, and then selects a marble. These two events are dependent because I took a marble from the bag, I didn't replace it, so now I have less marbles in the bag, which changes my second probability. So you'll notice how I wrote this. P of A and B is the probability of A. That stays the same no matter what, times the probability of B following A. That's going to be different than just the probability of B because now I have one less marble in the bag. So you will always decrease the denominator by one each time since one marble will have been taken out. So our first set of problems, a jar, and these are independent events, by the way, the first set. A jar contains 4 blue marbles, 3 green marbles, 5 yellow marbles, and 8 purple marbles. Once a marble is selected, it is replaced. Pause the video, calculate how many total marbles we have. Hopefully you calculated that we have 20 total marbles. Number 4, how do you know that this represents an independent event? Well, hopefully you recognize it in the directions. It says that a marble is replaced, so that makes it an independent event. So number 5 says find P blue then yellow. I did not use the word and here, but it's still going to be compound events. So what's the probability of selecting a blue marble and then a yellow marble? So to figure this out, we do the probability of blue times the probability of yellow. Blue is 4 out of 20. Yellow is 5 out of 20. I did reduce these. Now, if you're using your calculator, you can plug in 4/20 times 5/20. It will get you a final solution of 1/20. But again, you could also reduce the two fractions, especially if you don't have a calculator. Reduce 4/20 to 1/5, 5/20 to 1/4, and multiply straight across to get 1/20. Number 6, find the probability of green then purple. Well, find the probability of selecting a green marble, multiply it by the probability of selecting a purple marble. Green is 3/20, purple is 8/20. 8/20 does reduce to 2/5. If you multiply, you might get 6/100, but that does reduce to 3/50. I'm going through the calculations quickly because you can use your calculator to do that. Number 7, find the probability of purple then blue. So multiply the probability of purple, which is 8/20, by the probability of blue, which is 4/20. They both reduce to 2/5 and 1/5 respectively. Multiply across and you get 2/25. Let's do a few more independent event probability problems. A number cube is rolled and the spinner at the right is spun. Find each probability. These are independent events given that they don't impact one another. Number 8, find the probability of 4 and D. So you get a 4 on the number cube and a D on the spinner. So the probability of getting a 4 is 1 out of 6 since you have 1 4 out of 6 on the die. or the number cube. Probability of D, well, I had one section labeled D out of 8, so that's 1/8. 1/6 times 1/8 is going to get us 1/48. Number 9, find the probability of a prime number and a vowel. Please note that a prime number is a number that is divisible by only 1 and itself, so that includes 2, 3, 5, 7, 11, etc. Note that 1 is not prime or composite. That's important to realize. And that 2 is the only even prime number. So find the probability of getting a prime number on the number cube, multiply it by the probability of getting a vowel, which we'll talk about in a moment. So for a prime number, that would include that number cube landing on 2, 3, or 5. That's 3 out of the 6 sides. A vowel, remember, is A, E, I, O, U, or sometimes Y, and sometimes Y. I didn't include Y on here just so we wouldn't confuse this at all. A, E, I, O, U. Goodness, saying that way too fast. So that would include the probability of getting a vowel would be A and E, these two sections, which is 2 out of the 8 sections, or 1/4. So do 1/2 for the prime number, 2/8, which is 1/4 for the vowel, that's going to get us 1/8. Number 10, find the probability of an odd number and a consonant. So for an odd number, that would be the number cube landing on 1, 3, or 5. That's 3 out of the 6 sides, or 1/2. A consonant is anything that's not a vowel. So 2 of those sections were vowels, A and E. That means the other 6 sections are consonants. So 6 out of 8 for that probability, which is 3/4. Multiply straight across to get a probability of 3/8. Number 11, find the probability of an even number and B. So for an even number, that is going to be 3 out of 6. B, there is only one section labeled B out of 8, which is 1/8. So we do 1/2 times 1/8. When we reduce those fractions, that will get us 1/16. All right, I think we have a couple more, and then we are going to go right into some independent practice for you, and then talk about some dependent probability questions. A number cube is rolled, and the spinner at the right is spun. Find each probability. Number 12, probability of an even number and red. So an even number on that die is 3 out of 6, 2, 4, and 6. And then for this guy to land, the spinner to land on red, it's 1 out of the 5 sections. They should be equally sized. I made it as close as I could when I made this spinner here. It's probably not perfect, but we'll go with it. So you've got 1/2 times 1/5 to get 1/10 for that probability. Excuse me. Number 13, probability of an odd number and not blue. So the odd number is 3 out of 6, very similar to the even number, but not blue is 4 out of the 5 sections, everything that is not the blue section. So take 1/2 times 4/5. That will get us, if you have 4/10, that's great, but it reduces to 2/5. Number 14, probability of 3 on the number cube and yellow on the spinner. The 3 on the number cube is 1 out of 6. Yellow is 1 out of 5. Multiply those to get 1 out of 30. Finally, probability of 6 and not green. 6 on the number cube is 1 out of 6. Not green is 4 out of the 5 sections. 1/6 times 4/5 will get us 2/15. Again, if you get 4/30, that does reduce to 2/15. All right, now I went through that. Oh, not independent practice yet. I keep forgetting about these two. Let's do them quickly. Number 16, a number cube is rolled and a letter is chosen from the word soccer. Find the probability of an odd number and an E. Well, an odd number on the number cube, we've seen this many times, is 3 out of 6. The probability of E in soccer, there are 6 letters, and one of those is an E, so that's going to be 1 out of 6. 1/2 times 1/6 is going to get us 1/12. Number 17, a number cube is rolled and a letter is chosen from the word soccer. Find the probability of an even number and a C. Even number, again, on that number cube is going to be 3 out of 6. The C, though, this time, or in this case, we have 2 C's out of 6 letters, so that's 2/6. 1/2 times 1/3, when we reduce those, will get us 1/6. Okay, now it is time for you to try some independently. Pause the video, try these 3 questions. All right, hopefully you tried these three independent practice questions. A jar contains 5 blue, 6 green, 8 yellow, and 1 orange marble. Once a marble is selected, it is replaced. That means this is independent probability. Find each probability. So probability of blue, then yellow. For blue, that's going to be 5/20. Hopefully you knew that there were 20 marbles total here. Make sure you count those up correctly. For the yellow, it's going to be 8/20. I did reduce those to 1/4 and 2/5. You end up getting a final probability of 1/10. Hopefully you have a calculator where you can multiply these things. If you don't, again, try reducing them ahead of time, or at least try your best to reduce them. You should be able to reduce fractions at this point. Number 2, probability of orange, then green. Orange is 1 out of 20th. 1 out of 20, sorry. Green is 6 out of 20. 6/20 reduces to 3/10. Multiply straight across to get 3/200. Number 3, this one we didn't see one like it previously, so this is a good one. Probability of 2 greens in a row. Well, the first green is 6/20, second green is 6/20. They both reduce to 3/10. 3/10 times 3/10 is 9/100. So hopefully you did pretty well on this. Again, one of your assignments this week is going to include some practice on this, so you will get a chance to practice more of this independently. All right, so let's do some dependent probability questions. These are our last few. I know this video is getting kind of long. I'm getting tired of talking. I'm sure you're getting tired of listening. So probability of dependent events. A jar contains 4 blue marbles, 3 green marbles, 5 yellow marbles, and 8 purple marbles. Once a marble is selected, it is not replaced. Take a moment, calculate the total number of marbles. So hopefully you recognized we've got 20 total marbles here. It's really important to get that number correct from the beginning. How do you know that this represents a dependent event? Well, we know in this case, because the marble is not replaced, that these are dependent events. So number 19, find the probability of blue, then yellow. So find the probability of blue. That is going to be 4 out of 20. Then we want to find the probability of yellow, but after we took that one blue out, and we didn't take all 4 out, we just took one blue marble out, even though the probability is 4/20. Now we have 5 yellow marbles, but we only have 19 marbles left. So that denominator decreases by 1. So it's 4/20 times 5/19. That's 1/5 times 5/19. You can cross out the 5's here because we had a 5 here and a 5 here diagonally. You get 1/19 for your solution. Number 20, find the probability of green, then purple. So let's start off with probability of green. That is 3/20. But then for purple after green, we have 8 purple marbles, but keep in mind we only have 19 left. 3/20 times 8/19 is 6/95. And again, you may use your calculator to do that. Number 21, find the probability of purple, then blue. Probability of purple is once again going to be our 8/20. But blue after purple, we've got 4 blue, but again, we only have 19 remaining. 8/20 reduces to 2/5, multiply by 4/19 to get 8/95. You'll a lot of times see weird denominators with this because we decrease the denominator each time. Now 22 and 23, I put some stars next to these because this is a little different than our 2 greens in a row from a few moments ago. Find the probability of 2 yellow marbles in a row. Well, the first yellow, we've got 5 yellow marbles out of 20. So that's going to be 5/20. But then the second yellow, we only have 4 yellow marbles left and 19 total marbles. So notice how both the numerator and denominator decreased by 1 this time. 5/20 reduces to 1/4. We can cross off the 4's that are diagonally, and we actually get the same answer as we got for number 19 up here. That won't always happen, but we get 1/19. So I threw in another one of these. Find the probability of 2 green marbles in a row. Let's go back up above. We had 3 green marbles. So we start off with 3/20, but then we decreased both the numerator and denominator since I took one green out and didn't replace it. So it's going to be times 2/19. Multiply straight across, you will get 3/190. Again, for these, you decrease both the numerator and denominator since you took one of those colors out. I do want to mention that every time we start a new problem, we're going back to what we originally had in the jar or container. We're not continuing to decrease the amounts of each. Last two, we have three marbles that we're selecting here. So number 24 is blue, then green, then yellow. So for the blue, that probability is 4/20. For our green, that is 3/19, since we only have 19 left. And for our yellow, we have 5 yellow out of just 18. Notice how I'm decreasing that denominator by 1 every time. 4/20 reduces to 1/5. That's the only fraction that reduces. If you want to kind of cross reduce a little bit here, we've got a 5 on the bottom and a 5 on the top. That would get you 3 out of, you'd have to take 19 times 18. It does eventually reduce to 114. If you recognize that 3 and 18 both divide by 3, so you can cross off the 3 and make the 18 a 6, you can do that as well. Again, it's easiest if you have a calculator that you can just plug these in. Finally, number 25, find the probability of purple, then yellow, then blue. So for purple, this is going to be 8 out of 20. For yellow, it's going to be 5 out of 19 since you only have 19 left. And then for blue, we have three blue marks. Did I mess this up? Let me double check this. Oh goodness, we have a mistake here. So let's go ahead and fix this. I must have done green instead. So let's take a look. We've got purple, which is going to be 8/20. Let's confirm this. Okay, so we've got purple, which is going to be 8/20. We've got yellow, which we know is 5/19. And then for blue, this should be 4/18. So that's going to change this. Let me correct this. It looks like I did it as if this were green. Hopefully I didn't make a mistake on your guided notes, but this will be a 4/18. So this is going to change our answer a little bit because each of these is going to reduce a little. So looks like we have 8/20, which is going to reduce to 2/5. That doesn't change. 5/19 does not reduce, but I can cross reduce these fives. That will benefit us. So I'm going to be doing this without a calculator here. That could be fun. 4/18 divide top and bottom by 2 is going to get us 2/9. So this guy right here, I'm going to replace with 2/9. So we've got 2/9. We'll do this the best that we can, so bear with me. My apologies. This goes to show sometimes when we're typing things in too quickly, we make some mistakes. That happens at times. It's not the first, and it certainly will not be the last mistake. Let me just shrink these a little bit so it's not too overwhelming here. So we'll make this a 2/9. That's from the 4/18. Let's see if I can cross reduce here just to make things a little easier. Looks like I've got 2 times 2 on the top, which is 4. Looks like on the bottom we've got 19 times 9, which is going to get us, let me think that through, that should get us 171. So this should be 4/171. So let's cross this guy off. And again, my apologies here. This should be 4/171. That should not reduce any further. So final answer here, 4/171. At least I corrected that as we were working through. So again, my apologies for that one, but hopefully with all the other previous examples, you understood what was going on. So let me just repeat for this one. Probability of purple, we had 8 purple out of 20 total marbles. For yellow, we had 5 out of just 19 left. And finally, for your blue, we had 4 blue marbles out of 18 left. 8/20 reduces to 2/5. 5/19 does not reduce. And then 4/18 is going to reduce to 2/9. So multiply straight across, we should end up getting 4 out of 171. Assuming I made no other mistakes, I'll double check that at the end of this, and I'll make any notes if there was a mistake. Now, I did put in here some independent practice for you with dependent probability. Pause the video, give these 3 questions a try. All right, hopefully you paused the video and completed these three. This is our last set, and then we are done with this video. I know it's getting kind of long here. A jar contains 6 blue, 8 green, 7 yellow, and 4 orange marbles. Once a marble is selected, it is not replaced. Find each probability. So blue then yellow. Hopefully you recognize that we have 25 marbles here. 6 plus 8 is 14, plus 7 is 21, plus 4 is 25. So blue is 6 out of 25. Yellow is 7 out of 24. We cannot reduce either of those fractions, but we could cross reduce. We end up getting 7/100ths. Number 2, probability of orange, then green. Orange is 4 out of 25. Green is 8 out of 24, which reduces to 1/3. We get 4 out of 75. Finally, number 3, probability of 2 greens in a row. The first green is 8/25. The second green is 7/24. Neither of those reduces, although you can cross reduce. You will get 7/75. All right, I'm not going to hold you up any longer because I know this is a very lengthy video. I think you'll find the practice that you need to complete on this to not be too difficult, but feel free to go back to the video, go back to the guided notes at any point to remind you of how to do this. Thanks for listening.